Okay. Oh, before giving the stage to Tiziano, I want to acknowledge two previous fantastic PhD students, which are like kind of here, becoming grayer and grayer, that help us to establish the course. And in particular, I would like to acknowledge everyone that invested effort in preparing exercises of lecture for the time to come. So at the end of the course, in 10 years, there will be many, many names in the list. So, okay, stage to Tiziano.
Nice. So hi guys, I'm Tiziano, and we are going to discuss localization in the discrete case using the bias filter. So, what are the important steps to implement a bias filter for any kind of application, general? We have to know how to represent the state, and the state is the quantity that we want to estimate. It might be the robot position, but it might be also parameters of a manipulator, or whatever it takes. Thank you, Giorgio, for the volume. Also, how to represent the controls, which of course are related to the quantity that you want to estimate, and also on how to see the system evolve over time. Observation, related to the sensor that you're using, how to implement the transition model, and how to implement the observation model, okay? So this is a kind of a methodology, and you actually can apply the same methodology in a lot of problems in state estimation, generally. Least square, Kalman filter, particle filter, whatever. They all follow these kind of steps to be implemented. So that's our case. So we want to estimate the robot position given a map. We are in the discrete case, so the map is represented as a grid, and the robot position is actually the couple of indices, so rows and columns, which represent where the robot is. Really, really simple. Now we will go deeper in this image later on. So we have a map and we have the robot, so we have to model. The state is defined. We have to model the transition, and we will see the case where we have noise in the controls, so where we don't have noise in the controls. We will model the observation model, and then we will build the actual filter. So prediction step, update step, as the professor just explained it to us. So, as I said, the map is a grid, and we use this convention to say that if the value in the grid is 0, then the cell is free, so the robot can move inside those cells. If the cell is 1, we have an obstacle, so eventually the robot will crash against it, and it cannot move over it, of course. So that's the situation. So as I said, the state are the couple of indices where the robot is, and the controls, you can think about it as the arrows of the keyboards, so you can move up, down, left, right, but not on the diagonal, okay? And actually the robot is, the sensor with which the robot is equipped are bumpers on the 4 sides. So a bumper is a sensor that when you crash an obstacle, it gives you a measurement, like a binary measurement. 0, not hitting anything, 1, I'm hitting something.
It's a switch.
Switch, basically switch. So really, really simple. So you should find in the repo, sorry, there is like a mosquito here. You should find in the repo of GitLab this code, octave code, called 04 grid-orazio. And these are basically the steps that we are going to implement. I will show you directly the code, and then we will leave something for you to do at home this week. So you can see we have the set of observation, state belief, which represent our prediction. Please kill this thing. Yeah.
And you look at the screen.
Yeah. I prefer to look here. I prefer to look here. So, set of observation, this is our prediction. So we will update the state belief at the current step using the previous state and the control. Then we have the update step where we compute the state belief and the inverse normalizer to get the proper probability distribution. That's why the inverse normalizer is important. So, transition model. Okay, so let's give a little bit more details. So it takes a previous state, which is represented by a row and a column. You need a map, because you have to know if you can move in the target cell or not. And you take a control input. In this case, we hard-coded these quantities, which are represented by the beautiful octave language as the arrows, so up, down, left, right. And you can also use WSAD, like in video games, basically. And they are coded by those values. God knows why, but we use it, and that's it. So, given that, we get a transition probability matrix. Now, if you have to guess, what's the size of this matrix? I can open, like, to see the comments, if someone reply.
What do you want to do?
The YouTube.
No, I'm monitoring it.
Ah, okay.
So I will be monitoring the questions on YouTube. So
Okay,
if you have
that's done.
any thoughts, sadness, just write them in chat.
Okay, just to answer what I asked before, otherwise it became everything too slow. These matrices have the same size of the map, because the next state might be any state in the map. We don't know. We have to estimate it. And the value inside will be the probability that the robot is in that specific cell. So actually, this transition is as big as the map in the discrete case. So that is how input and output works in the transition model. We have to describe the noise model eventually to this transition, because it's a probabilistic transition model. So first we will speak about the case without noise. So the control is not affected by anything. If I press right, it will go right with probability 1. So this means that I know exactly how to place my probability inside those tables. If I start from 3, 4 and I move right, I know that I am in 3, 5. That is, okay? As easy as possible. So we add some motion constraints, so we can move one cell at a time, we cannot move on the diagonal, and we cannot move 2 steps forward. In this case, the probability will be 0 because I cannot do that motion. So the constraints are represented by, I give a command which the robot is not able to realize, so I say the transition is 0, I'm not moving, okay? That's the constraint that I put. Also, another constraint is the fact that if I have an obstacle, I cannot go over it, I will crash it. So if I tell the robot to go right, and on the right a cell is occupied, I will stay in the same state with probability 1, as before. So the probability of my transition is actually 0, I cannot go to the right. So these are how the constraints are implemented. So this is the row that I want to reach, this is the row where I'm coming from. If the translation, so the amount of motion that I have, is greater than 1 on the rows, or is greater than 1 on the columns, because I can move just one of it, I will not do anything. So the robot will not move, okay? So this is a sort of velocity constraint, like joint limits, for say, okay? Something like that. Let's try noise-free state case. I think this, you can read it. This is the from. Then if I move up, I increase the rows because I go this direction. If I go down, I go this direction, so I decrease the rows. If I go right, sorry, I will increase the column. If I go left, I will reduce the columns. Motion feasibility, these are all the checks. I will not go to details. I think you are able to read. Of course, the row have to be a positive number. It cannot exceed the number of rows in the map. Same for the columns, etc., etc., etc.
Mention that they have all the programs.
Yeah, I tell it at the beginning. Yeah, you have available everything.
I recommend to pull the repo now because I put everything yes.
Nice. So guys, pull right now. Yeah, what I was saying? Nothing. Okay. So, also here is another check, always for motion feasibility, and this is an integral part of modeling the transition of a robot. You have to take into consideration the environment, velocity limit, etc., 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 etc. So, a big part of this program is actually made by implementing all the constraints. And this, for example, is the case where you have one occupied cell in your trajectory. So you basically stay fixed where you came from. Oh. Okay. So now let's go to a little bit more of a real case. So in modeling the control.
Like, perhaps, I can't. So once you want to model a dynamic system, the very first thing that you do, even in this simplistic case, is that you just a very simple thing that you have to do at the beginning is to design it as if it was a simulator. Don't think about the noise. Don't think, just imagine it noise free, and just imagine that the system is doing exactly what it's supposed to do. Okay? So this is a very simplistic code where you have a robot moving in 4 directions in a world which is consisting of obstacles. If you move against the obstacle, the robot doesn't move. If you are close to a wall, the bumper will say, hey, bump on the back, on the side, on in front of yeah. Yes? Guarda.
Yes.
Quello lì. Muovi il mouse?
Mm-hmm.
Nel posto. Ok. So like, imagine the very simple, easiest thing that you want to do when you design an application or anything is to describe your system at the beginning as if it was noise-free. Okay? So write a simplistic, just a stupid video game with 4 arrows where the robot moves. So if you tell it go on top, it moves on top with no noise. If there is not a bump. Go on the right, moves on the right with no noise. That's exactly what we have been doing, modeling this simple world. Okay? You start from that, and then later on, you make it a little bit more complicated. But remember, when you will design a system, a filter, an estimator, or whatever, you normally make a lot of mistakes. We all make a lot of mistakes. And then the very first step that you do is to feed it with synthetic data and the perfect model and very, very small noise and figure out whether it works in this setting. If it doesn't work in that setting, then there is something wrong in the concept. And then you continue like adding complexity. So you always start from the easiest thing you can do and you add a little bit of complexity at a time. This was like the message. Now what Tiziano said to you is basically we're modeling the perfect system. And then on top of this perfect system, then we will be adding noise. Okay, this was the message of the elder here in the group. No, because they don't see the slides.
No, yes, I guess.
Do they? No, they see it, but they don't.
Ah, you have the double settings. Nice. Okay. So, that was the ideal system that the professor was talking about. Now we will add noise in the controls, of course. And for example, what we say is that if we impose a motion, Carino, come on, excellent connection.
No, say hi.
Guys, someone write on the chat if you see us.
Ok.
Spero io.
È me stesso che non funziona.
Ma col tuo telefono funziona già. Okay, so I was saying we add noise. So if I impose, for instance, a right motion, the robot have a probability 0.8 to realize it, so to actually move on the right. Then you have a 0.1 probability to go top right, 0.1 probability going bottom right. Consider that these diagonal motion are not included in the transition model, so they are not feasible motion in theory. You cannot impose to the robot to go diagonal. So you can just go right, left, top, right. But the robot now, to the noise, can go also diagonal, but you cannot model.
Just imagine the slippery wheels.
Yes, it's like the case that you have an actual robot with wheels. You try to impose it to move forward 1 meter. You imagine that your wheels are not exactly equal and you're actually a little bit turning. That's the effect that you have. And this happens usually when you don't have a proper calibrated platform, for instance, just as an example. So, and of course, this behavior is symmetric for each motion. Like if you go up, you will go up right, up left with probability 0.1. Okay? So it's sort of a more realistic noise model. Of course, if you have an obstacle, the probability is 0 because we are always subject to the constraint of the robot and of the constraint of the environment. Consider that this probability don't sum to 1. You're just zeroing the component on the bottom diagonal if you have an obstacle there. Of course, that's a simplification, but we will live with that, okay? Same here, same constraint as before. So if I impose the robot to move right and right is an obstacle, this is an extreme simplification. I will just say that the robot stays in the same position. Even if the diagonal cells are free, I will keep it fixed. Clear? this is how we implement it. So you check basically rows and columns of your destination, and you fill with the probability the transition matrix, depending on the starting location and the motion. Easy peasy. Like, check the code out. Like, if you read it, it's much easier than if I repeat it to you, but that's just the implementation of what we just said. And what I want to point out for the transition model, also if you see the theoretical slide of the professor, is that the transition model is always increasing your uncertainty. It's never reducing your uncertainty. Why? Because basically you are marginalizing over the previous state. And marginalizing means summing all the value of that gigantic cube and like to splash it in this direction. So you are summing everything, and the value of the probabilities is of course uniforming over the whole grid. So if you are doing transition, 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 you are being more and more delocalized. You are not more localized because integration, and second, you are introducing for each step the noise of the controls inside of your estimate. So you are continuously adding noise. To reduce this uncertainty about our estimate, we need an observation. So this is a non-direct observation of our state. And in this case, we have 4 bumpers. So by observing the external environment, we get the indirect information about where we are. So we have 4 bumpers in the 4 sides of the robot, and these are all the possible readings that we can get. So no bumpers, everything is 0. Bumpers on the right, we have a 1 there. 2 bumpers at the same time, 3 bumpers at the same time, 4 bumpers at the same time. This is just a logical table with zeros and 1 and 4 variables. Okay? And this is how we model the probability of each observation, for instance. Okay? So, retrieve the observation by taking the ground truth. The state ground truth means the current estimate, I suppose. The map and the observation, and then you get the current probability of, given the current state and given the map, which is assumed to be known, what's the probability of observing this type of observation? What I will observe if I'm here in this point in the map. That's the idea. Then I compare it with the measurement and I get the probability on how likely is this state. How I'm likely to be in this state. So that's the meaning of this guy over here. And this will reduce my uncertainty. So we add also noise inside the observation model. This is pretty logical because if you think that all sensors introduce noise in a model, even a laser scanner on a camera, you have always some noise in the pixels or in the readings of the laser, in the encoders, whatever. So to make this thing more real, we add a sort of probability distribution, a sort of noise model. And in this case, we have the 0.2 probability to get a false positive, which means I detect something that was not actually there. Like my bumpers give me a 1, but I'm in the middle of completely free space. And with probability 0.8, the measurement is correct. Is that right? Like, is that clear? Sorry. Check chat. Check chat.
Chat says works, but it was 11:26. So.
Okay. Nice. We're with a little bit of delay. So, and that's how it's implemented. So this is your observation probability. If the cell is actually occupied, you put 0.8, otherwise you put this fake 0.2, even if it's not occupied. Like if it's not occupied, you put it 0.2, etc., 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 for all the 4 bumpers. So up, down, left, right. You can have these false positive readings, let's say. So, this is the implementation of all the different steps, more in detail, like how the probability is actually propagating during the prediction and the observation. So at the beginning, we don't know anything about the state, so we don't know where we are. So what we do is that we build a uniform probability distribution. So we take the number of free cells, we define the initial value as 1 over, because of course all the cells have to have equal probability, and then we initialize the state belief as a matrix as big as the map with the corresponding probability value, which are uniform over the free cells. Because the only knowledge that we have is what cell is free and what cell is occupied. So this is actually how a tabular uniform representation is implemented. And that's our initial belief. So that's the prediction. So let's revise the formula again. Starting from here, we have this guy, which is our three-dimensional tensor, like ignoring the measurement here. And then we are marginalizing over the previous state. It means we are summing up all the entries in this cube about our previous state. So this can be written as this thing. So I have my prediction model and I have my previous belief. So I have to multiply them and plug it inside. So that's what I'm going to do. So state belief plus equal transition model pair state belief previous. So I take the previous table, I pick the corresponding probability value, I compute the value of the transition model, which will be this summing, I multiply them, and I add to the state belief. In this.
Professor, one small thing. This is a system that has a discrete state, right? So it has a fixed number of states, clearly, right? Like for our convenience, we just like displayed these states in a matrix indicating a row and a column. But it would be perfectly equivalent if you just enumerate the states. And in fact, in this matrix, there are configurations, there are cells which are not valid, which corresponds to the cells where the obstacles are. Because we know that the robot cannot be in the obstacles. Okay? So there will be also some row call, some cells of this matrix which will constantly have a zero value. Okay? This state belief previous row call is equivalent to this B of xi, only that instead of having a unidimensional index, we have two indices here for the state. This is perfectly equivalent. And the transition model, well, this row call denotes basically the state, the index of the state, no, of the current belief, and this denotes the control input, which is our u, and map is the the information I need in order to compute the transition. Is regarded as prior knowledge because the location of the free cells will influence the probability of going somewhere else or not, depending on the presence of an obstacle. Okay?
So, always point out here that you are sum equal something. So the uncertainty of your current belief.
Maybe we need to explain more why we have this state belief this way, because this transition model requires a matrix, right?
Yeah, I showed it before.
Ah, okay.
The state belief is a matrix.
No, the transition model is a matrix.
Also, like, yeah, but we show it here. I explain it in this step. Wait, where is it? No.
Aqua. Okay. Ah, okay.
I see it here.
Okay. Okay. So
come back. Observation. No. This guy.
Yeah. Okay. So one could precise. We take one particular step, and the transition model will return us a matrix, an assignment, a density over possible next states that I could reach starting from the state in row call. Okay? And this will be a distribution of a state. I take this entire distribution, this entire histogram, right? And I multiply it by the probability of actually taking that histogram. And then I sum it up in a cumulative manner in the state belief. Okay? Take, like how likely is it? How likely is it that I pick it up and sum it up? And then you do this in one single operation. It's an alternative implementation, not like one-to-one with the slides.
Then the update step, which is represented by this formula over here. So we basically are integrated information from our observation model, and then we have this normalized, which we are not interested in. It's just making this belief a proper probability distribution, actually. And how is that implemented? This is the output of our transition model. So a distribution over the actual state after integrating the previous state and the controls. This is the previous belief, of course. Marginalize it. So we have to multiply by this value. So assuming that you know the state, in this case you know also the map, what's the probability of seeing this bumper on, this bumper on, this bumper on, this bumper on, okay? So, oh, Jesus, here. So I give it the map, I give it the current location of the robot, so xt, row column, and I give the observations. So bumpers 1 is up, bumpers 2 is 0, blah, blah, blah. And then I output a probability value, so between 0 and 1, and then I scale the state belief in index, row, and column. So I do a for loop over my representation of the state, which is a table. For each of these cells, I evaluate the observation model using the current observation, and these values is used to scale the corresponding state belief. So in this step, I'm actually reducing the uncertainty. I'm not summing up, I'm multiplying a probability value, which is always less than 1, typically. And it will be higher just for the states which are highly probable to be realized for that observation. And here I compute also the inverse normalized, so that at the end I can make my table a probability distribution, of course in a tabular form. So this is how to test it, like to have a look at it. I will try to do it online, which would be impossible for sure. So here, 04 grid-orazio. And then you have this folder where we put a map.txt, which is like a sequence of 0 and 1, as you can imagine. Really, really simple. You can make it up really easily. And now I will move this guy here. Maximizing. Okay, so that's our initial condition. So you don't see anything. The probability is uniform for everyone. Now if I move, the blue represents the observation and the red is the current position, the real position of the robot. And as you see in this case, here we have a false measurement. Like here there is anything and I still observe something. And this is how the probability distribution change. So if I continue to transition, taking just false measurements, you see that I'm not getting a pretty good estimate. Now, I'm perfectly localized. I continue to get observation until I basically get all the probability concentrated in a single cell. Now I will show you the effect of doing just transition. Depending on what I eat. So you can move, actually I was thinking it was the arrows, but it's WSAD. So you can check it out, try to modify stuff and see how it's working. If I go in this tunnel, I will keep localized because I observe all the time at least two bumpers, let's say. So actually what we would like you to do is to modify the program.
Now what they have to do like is to first run it.
No, it's already programmed in this one.
Yeah, but they have to run it to the familiar with it.
Yeah, I know, but they can do it even at home. Like yeah. It's not a big issue. Like I don't think that they will start to do it right now. So this can be like a sort of formative exercise because you have to modify two aspects. One is the state and the other one is the transition model. Of course, also the observation gets slightly modified, but not so much. So the state now is not only the position of the robot, but you have also an orientation. And in particular, you can move just forward and backward and rotate on the spot. So if you, I want, what?
90 degrees.
Yeah, if you want to go left, you have first to rotate, then go forward. So you have to add 2 motions to reach the same state. So these are the new primitives. At the same time, you have to modify the transition model, and you have to include the noise not only in the translation part, so going up and down, but also in the rotation. An example might be, I tell you to rotate 90 degrees to go left, but there is a 0-1 probability that you finish like that, or you finish like that, or you finish like that. Okay? And then discover how the state changes, how the observation changes, and how to modify even the constraints, because you can modify also the constraint. That's not an homework, that's just a suggestion for you to do to get more familiar with this filtering framework. But then if you have any question in implementing it, you can contact me by email. I think I will put my office hour Tuesday from 4 to 5.
Yeah, I mean, I would say that we can invent something for the remaining part of the lesson, and we can, because we have basically no interactions with the student, and this is a drama for us, because we don't figure out how they're following, and also for you, I guess, because like it's less easy to attend the things. So we might, I would, because we have lesson until, we have this room until 1, right?
Yeah, but in 1 hour, you want to open a gigantic Google Meet with everyone?
No, I want to, well, we could actually open a Google Meet right now where they do the things, because normally our lessons can change the profile, change the... Yes? Oh, okay, yeah. Because normally we used to have the students, which is you, in the lecture hall with the laptops doing the exercises, and so we could check over them. Now we can do it, but with 2 people. Actually, we have 2, we doubled, no? Since the last time. Now we can do it with the people present in the lecture hall, but and we would like to do it also with you at home. So while they start and try to get familiar with these things, we have 1 hour to devote to them. So I will open a Google Meet. I will send the link to the mailing list of the...
Which is not ready yet, because we're still waiting for everyone to open the form.
Doesn't matter, we have the one registered. No? I would open a Google Meet into the a Google Meet session, and then we will be here, you will be here with the laptops, and you can start doing the exercises, and if you have other questions, you just ask them to us. Okay? I hope you like this format. Of course, this part of the lessons, I don't know whether we will register or not, because it's more individual interactions, but if there is any question that pops up to be relevant for everyone, we will discuss it later on in the lesson. Now, for sure, you will have problems downloading or running. I mean, some of you, not all of you, will have some problems in downloading, running, and so on and so forth. So now we close the streaming. You will receive a link to a Google Meet that you can log in and basically be part of the interactive lesson. What I ask you to do is to download the code and test first of all that the stuff that Tiziana has shown you works. You do this by going in the repository where you downloaded the slides and type git pull, and that will refresh the slides. And then we will basically give you remote assistance until 1 in doing the state. And also if you have additional explanation to be asked and so on, we will achieve this way the interactive part of the lesson. Potremo pure chiudere lo streaming, no?